Our galaxy is already hard to hold in the mind. 100 billion stars, 100,000 light-years from edge to edge, more than anyone could count in 1,000 lifetimes. And yet, if you set it beside the thing some astronomers think they have found, the whole of it would shrink to something like a single grain of sand resting on an empty beach. That thing is called the Hercules-Corona Borealis Great Wall, traced across the sky from the flashes of dying stars, and it may stretch close to 10 billion light-years from one side to the other. If it is real, it sits right at the edge of what our best theory of the universe says should be allowed to exist. How big is too big for the cosmos to hold? "10 billion light-years. That is the claimed length of the Hercules-Corona Borealis Great Wall. And to feel what that number does to you, you first need to know exactly what 1 light-year is. A light-year is a distance, not a stretch of time, even though it carries a calendar word inside it. Light is the fixed speed limit of the universe, about 186,000 miles every second, fast enough to circle the Earth 7.5 times between 2 ticks of a clock. Let it run at that pace for a full year and it covers close to 6 trillion miles. If you tried to count to 6 trillion, one number a second, never stopping to sleep, you would run out of human history long before you finished. And the wall tonight is 10 billion of those lengths, laid end to end. Climb outward from your own chair, and every familiar distance shrinks to nothing on the way up. The Earth is about 8,000 miles across, and light crosses the whole planet in under a 20th of a second, faster than a blink. The Moon is 250,000 miles out, and its light takes a little over a second to reach you, so the Moon in your window is always a heartbeat behind the present. The Sun lies 93 million miles away, 8 minutes off at light speed. If it went dark this instant, you would sit in full sunlight for 8 more minutes before the sky had any idea. Past the farthest planets, light still needs only a few hours to clear the entire solar system. Everything we have ever named, every world and moon and comet, fits inside a bubble light crosses before a single day is done. Then the emptiness opens. The nearest star past the Sun sits more than 4 light-years away. Shrink the Sun to a grain of sand on a table, and the next grain rests a few miles down an empty road, with bare table the whole way. Space is built mostly from that gap. The stars are rare points, and the dark between them is the ordinary state of things. Take 100 billion of those stars, or by some counts closer to 400 billion, and bind them with gravity into one slow-turning disk. That disk is the Milky Way, roughly 100,000 light-years from edge to edge, and we sit a little past halfway out, on a quiet spur of one arm. Light that crossed the whole Earth in a flicker would need 100,000 years to cross our galaxy once. Every star you have ever seen with your own eyes, every point in every constellation, lives inside this single disk. The Milky Way is not alone. Our nearest large neighbor, Andromeda, floats about 2.5 million light-years away, close enough that the two of us are slowly falling toward each other. Both belong to a small huddle called the Local Group, around 10 million light-years wide, which is itself a suburb of something far larger. That larger thing is a supercluster named Laniakea, a flowing basin of 100,000 galaxies stretched across roughly 500 million light-years. We are already at distances where the Milky Way itself has dissolved into the texture, one bright thread among 100,000. For a long time, superclusters were thought to sit near the very top of the ladder, a structure climbing much higher than that, pressed against the limit of what the universe should be able to assemble at all. One of the largest things ever charted before our subject tonight is the Sloan Great Wall, a band of galaxies running about 1.5 billion light-years long. When it was mapped, astronomers treated it as something near the ceiling, an object so vast it strained the rules. Now set our wall beside it. The Hercules-Corona Borealis Great Wall, traced not from ordinary starlight but from the death flashes of distant stars, is claimed to stretch 10 billion light-years. That is not slightly larger than the Sloan Great Wall. It is close to 7 times longer, a single feature dwarfing the very object that was already thought to sit at the edge of the possible. Stack our galaxy against it, and you would need 100,000 Milky Ways in a line to cross it once. The disk holding every human story ever told becomes a fleck you would lose between 2 heartbeats. Nothing about this object is solid. It is not a barrier, not a sheet of material hanging in the dark. It is a region where galaxies and the violent bursts that mark them appear far more crowded than the empty stretches around them, a vast loose concentration drawn out across the sky. The wall is a density, not a slab. But a density 10 billion light-years long is still one connected feature, and a single feature that size is exactly what has to be explained. Size by itself is not what keeps cosmologists arguing, because the universe is full of enormous things that break no rules. Galaxies are huge, clusters of galaxies are larger, and superclusters like Laniakea are larger still, yet every one of them sits comfortably inside the theory. The wall is different in a way that changes what kind of object it is, not merely how big. At 10 billion light-years, it stops being a large thing inside the universe and becomes the size of a serious fraction of the universe itself. A structure is allowed to be vast. What it is not supposed to be is a vast slice of everything that exists, and that is the line it appears to cross, which is why the real trouble begins only when you stop measuring it against galaxies and start measuring it against the whole of what we can see. The observable universe is about 93 billion light-years across. Hold that next to the age of the universe, and something refuses to add up. The universe is roughly 13.8 billion years old, and light sets the fastest pace anything can travel. So the farthest any light could possibly have come to reach us is 13.8 billion years worth of distance. A sphere built from that travel time would be about 27 billion light-years across. Yet the real figure is 93. The visible universe is more than 3 times wider than the distance light has had time to cross. Space itself has been stretching the entire time the light was in flight. When a beam left a distant galaxy 13 billion years ago, that galaxy sat much closer to us than it does now. While the light crawled toward us at its fixed speed, the space between us and the source kept swelling underneath it, carrying the source farther away even as its old light continued inbound. The light arrives carrying a snapshot of where the galaxy used to be. The galaxy itself, if it still exists, now sits far beyond that, pushed out by all the expansion that happened during the journey. Picture a loaf of raisin bread rising in an oven. The raisins never move through the dough. The dough swells, and every raisin drifts from every other raisin, the farther ones separating fastest. Galaxies are the raisins, space is the dough, and nothing travels through space to cause it. The space between things is simply getting larger. Run that across 13.8 billion years, and the edge of what we can see ends up not 27 billion light-years away, but about 46 billion in every direction, 93 billion from side to side. We know the expansion is real because the light carries the fingerprint of it. As space stretches, the light waves crossing it stretch too, sliding toward the red end of the spectrum, and the farther the light has traveled, the more stretched it arrives. Measure how far a galaxy's light has been shifted toward red, and you read off how much the universe has grown since that light departed, which converts straight into a distance. Reading expansion out of color is how nearly every distance past the closest galaxies is actually measured, including every distance that defines the wall. So the word observable has to be taken seriously. It does not mean the edge of the universe. It means the edge of what light has had time to deliver to us since the cosmos first became clear enough for light to travel at all. The farthest thing we can detect is not a boundary but the oldest light in existence, set free about 13.8 billion years ago, when the cooling universe first let light run, now reaching us from a present distance of some 46 billion light-years. Past it, the universe almost certainly continues, possibly without end. We sit inside a bubble made of everything whose light has had time to find us. Now bring the wall back and set it inside that bubble. The Hercules-Corona Borealis Great Wall is claimed to span 10 billion light-years, and the bubble of everything we can see is about 93 billion across. A single structure, one connected over-dense region, reaches roughly a tenth of the way across the entire observable universe. That is not a tenth of our galaxy or a tenth of our supercluster, but a tenth of the whole visible cosmos, end to end. Measure the things we already called enormous against the same ruler. Laniakea, the supercluster that holds the Milky Way and 100,000 other galaxies, spans about 500 million light-years, which against the full width of the visible universe is roughly 1 part in 200, a speck on the map. The Sloan Great Wall, long treated as near the ceiling of possible structures, covers a bit more than 1 part in 60, still only a local feature. The Hercules-Corona Borealis Great Wall, if the measurement holds, covers something near 1 part in 9. It is not a feature on the map of the universe. It is a feature the size of the map. The number deserves one honest qualification. Distances at this scale are slippery, because the expanding space we just traced means there are several competing ways to define how far something is, and they disagree by large amounts. The figure of 10 billion light-years describes the wall's longest reach across the sky and back through time, and depending on exactly how that reach is defined, careful estimates push it somewhat up or down. This object has no clean tape measure length the way a table does. What survives every reasonable way of measuring it is this. Even at the conservative end, it is the largest single structure ever claimed, and it occupies a fraction of the cosmos that nothing else approaches. That fraction is the whole problem. A small piece of the universe can be lumpy and uneven without troubling anyone, the way one field can be rocky while the country around it is, on average, smooth farmland. But once a single clump grows to a tenth of everything there is, you can no longer call it a local bump. It becomes a property of the universe as a whole, large enough that the rest of the cosmos has to be arranged around it. A universe with a structure that big inside it is a different kind of universe than the one our equations were written to describe. The fraction also collides with the calendar. Light from the far side of this wall has been traveling for billions of years, so we are seeing the structure not as it is now, but as it stood when the universe was young. A connected object reaching a tenth of the way across the visible cosmos, already assembled in that early era, raises a question that size alone never could. There may simply not have been enough time, since the beginning, for anything to grow that large. So we have moved past size into proportion, and proportion is what turns a record holder into a problem. 10 billion light-years is not just a big number. It is close to a tenth of all the room there is, held by one thing, seen as it stood near the dawn of everything. Which leaves a stranger question waiting underneath all of it. If this structure is truly that large and that far, how did anyone find it at all, when it is far too vast and far too faint for any telescope to simply look up and see? You cannot photograph the Hercules-Corona Borealis Great Wall. No telescope ever built could frame it. And even if one could, the ordinary galaxies that make it up are far too faint, at 10 billion light-years, to chart across a patch of sky that wide. To map something that distant, you need beacons, objects so violently bright that their light crosses most of the universe and still arrives strong enough to pin down. The brightest beacons that exist are the deaths of massive stars, and we call them gamma-ray bursts. A gamma-ray burst is the most luminous event in the universe since the beginning itself. For a few seconds, a single one can pour out more energy than the sun will radiate across its entire life, the whole 10 billion year span of its burning, released in the space of one slow breath. During those seconds, that one dying star can outshine every other source of gamma rays in the sky combined. Nothing else in the present cosmos comes close. The violence has a specific cause. When a star far heavier than the sun, something like 20 to 30 times its mass, finally exhausts the fuel in its core, the core has nothing left to hold itself up against its own weight. It collapses in under a second into a black hole. The outer layers come crashing inward after it, and as that matter spirals down, it forms a searing disk around the new black hole, spinning at enormous speed. From the poles of that disk, twin jets of material are flung outward at very nearly the speed of light, more than 99% of it, narrow and ferocious. The jets bore straight through the body of the dying star and break out into space, and where they tear free and slam into the gas around them, they radiate the flash of gamma rays we eventually catch. That narrowness is the key to seeing them so far away. The energy is not sprayed in every direction but focused into thin beams, the way a lighthouse gathers a dim bulb into a blade of light that carries for miles. When one of those beams happens to point at the Earth, we record a burst. When it points elsewhere, we see nothing at all, even though the star died just the same. We are catching only the small share of cosmic deaths whose beams sweep across us, and even that share lights up detectors built to watch the entire sky. We learned they existed by accident. In the late 1960s, satellites were placed in orbit to watch for the gamma rays a hidden nuclear test would release, a way of policing weapons treaties from space. They began recording flashes that came from no test on Earth and from no direction on Earth at all. The flashes came from deep space, from every part of the sky, brief and never repeating. By 1973, the work was published, and a new kind of object entered science with no explanation attached. Flares arriving out of the dark with no known source. It took decades more to trace them back to the collapse of distant stars. A flash by itself is only a direction in the sky. To turn it into a position in the universe, you have to know how far away it is, and the burst will tell you if you move quickly. After the gamma rays fade, the jet keeps plowing into the surrounding gas and glows for hours or days. First in X-rays, then in visible light, an afterglow that lingers long enough to study. As that afterglow shines through the gas of its home galaxy and the space beyond, certain wavelengths are absorbed, leaving dark lines stamped across its spectrum, and those lines arrive shifted toward the red by the expansion we traced before. Read the shift, and you read the distance. Each burst becomes a pin driven into the three-dimensional map of the cosmos, marking not just a direction but a depth. The logic that built the wall follows from this. A gamma-ray burst marks the death of a massive star, and massive stars form and die where there is matter to make them, inside galaxies, along the crowded regions where gas has gathered. So, a burst is not a random spark. It is a flag planted wherever the universe was busy building and destroying stars. Map enough of these flags, across enough sky and enough depth, and the scattered pins begin to trace the rough outline of where matter itself is concentrated, out at distances where single galaxies are far too dim to survey one at a time. The bursts are flares going off in a dark room, and each one briefly shows you where the furniture stands. This is why these particular objects, and almost nothing else, could have revealed a structure on the scale of the wall. Ordinary galaxy surveys run out of reach long before 10 billion light-years. The bursts do not. They can be seen from the early universe, some recorded from eras when the cosmos was a small fraction of its present age, and each one carries its own distance written into its fading light. They are the only marker both luminous enough to cross that gulf and precise enough to place. There is a cost to using them, and an honest map has to admit it. Bursts are rare. A given galaxy might produce one only once in hundreds of thousands of years, and we see only those whose beams point our way. So the map they draw is not a smooth photograph, but a scattering of dots, sparse and uneven, with wide unlit gaps between the flares. Reading a structure out of dots like that is delicate work, and it leaves room for the eye and the mathematics to disagree about what is truly there. For now, the method stands as the only window we have onto matter at these depths. When the pins were placed and the distances read, one region of the early universe held far more of them, packed far more tightly than any stretch of sky has any right to. It was a pile of deaths too large and too concentrated, sitting in a place where the universe was still young. The instrument had found its structure. The harder question was whether the universe was allowed to contain it. There is a size at which the universe is supposed to stop building. Above it, structure is meant to give out, and everything smooths into sameness. Astronomers have a half-serious name for that ceiling. They call it the end of greatness, the scale beyond which there are no greater things, only the average texture of the cosmos repeating. It sits at a few 100 million light-years. Take a volume that wide anywhere in the sky, and it should hold the same rough mix of galaxies, clusters, filaments, and voids as any other volume that wide, no matter which way you look. The wall we have been tracking reaches 10 billion light-years. It does not approach the end of greatness. It runs past it by something close to a factor of 30. A ceiling exists for a concrete reason, and it begins with what builds large structures in the first place. Only one force does the work, and that force is gravity. Gravity alone gathers matter across cosmic distances, drawing slightly denser regions denser still over time, but its reach is not instant. Its influence spreads outward at the speed of light and no faster. So in the finite time since the beginning, the pull from any one region can only have touched matter out to a certain distance. Two patches of the universe farther apart than that have never been able to feel each other at all. They have had no time to coordinate, no way to fall together into one thing. There is a hard limit on how far the organizing hand of gravity could have reached, and that limit caps the size of anything gravity could assemble. A second reason is written into the universe's first light. When we look at the oldest glow in the sky, the light left over from the early cosmos, we find it almost perfectly smooth, the same temperature in every direction to about 1 part in 100,000. Those faint ripples, 1 part in 100,000, are the seeds. Every galaxy, every cluster, every wall grew from those tiny early differences in density, amplified across billions of years as gravity drew the slightly fuller regions fuller still. The exact pattern of those seeds can be measured, and from it, the theory predicts how large an overdense region should be able to grow. Small clumps are common, larger ones rarer, and truly enormous coherent ones not merely rare but vanishingly so, their likelihood falling off a cliff as the size climbs. A coherent overdensity 10 billion light-years across sits so far out on that curve that the standard statistics leave it essentially no room to exist. Nobody claims the wall is held together by gravity the way a cluster is, and that distinction matters. An object that large could not possibly have pulled itself into a bound hole, because the age of the universe is far too short for gravity to have drawn matter across 10 billion light-years even once. What is claimed is gentler and stranger. The wall is a coherent pattern, a region where the bursts and the galaxies they mark sit more thickly than the surrounding cosmos, threaded together as one extended concentration rather than scattered at random. But this is exactly what the seed statistics forbid. Even an unbound pattern that large is the kind of coincidence the standard model assigns almost no probability to. The trouble is not that the wall is glued together. The trouble is that it is correlated across a distance where nothing should be correlated at all. The ceiling is not only an argument on paper. Run the standard model forward inside a computer. Seed a virtual universe with the same ripples we measure in that first light. Let simulated gravity build structure across billions of years, and the largest things that emerge top out in the same range, from a few 100 million up to at most around 1 billion light-years. The biggest structures charted before the wall, the Sloan Great Wall among them, sit close to that simulated limit, pressing on it without clearly breaking it. They are the giants the model calls barely possible. The wall keeps no such company. Even granting the ceiling its highest reasonable value, it overshoots by nearly 10 times, standing far above the tallest structure any simulation reproduces from the seeds we actually observe. It does not nudge the edge of the allowed and slip through. It stands deep in territory the equations describe as effectively empty of such things. And it does so while being seen in the early universe, when there was even less time for anything to have grown, which only sharpens the problem. The phrase, "if the measurement holds," is doing real work here. The whole tension depends on the wall being a real, coherent object and on its size being near the claimed 10 billion light-years. If both of those are true, the conclusion is not that we have found an unusually large cluster of galaxies. The conclusion is that the model we use to describe the universe at its largest scales is making a prediction the universe is ignoring. One of the foundations is cracked. Either our statistics for how structure grows are wrong, or our census of the bursts is misleading us, or the universe at the largest scales is not built the way we assumed. None of those is a small repair. That last possibility reaches all the way down to the single assumption the rest of cosmology is built on: the end of greatness, the predicted ceiling, the expectation that any large volume looks like any other. All of it rests on one rule we have quietly taken for granted from the start. The rule says that on the largest scales, the universe is the same everywhere, in every direction, with no special places and no privileged points. It is the assumption that lets us write a single set of equations for the whole cosmos instead of an impossible separate description for every corner of it. A structure 10 billion light-years long does not only break a size limit. If it is real, it puts a crack in that rule itself, and that rule is the thing we have to look at next, because without it, the science of the universe does not work at all. Modern cosmology rests on a single assumption, and almost everything we claim to know about the universe is built on top of it. The assumption is called the cosmological principle, and stated plainly, it says this: on large enough scales, the universe is the same everywhere and looks the same in every direction. It is not something we proved before we started. It is the premise we had to grant ourselves in order to start at all. Without it, there is no map of the cosmos, no age of the universe, no Big Bang as a single coherent story. With it, the whole thing becomes describable in a few lines of mathematics. Everything depends on whether it holds. The principle is really two claims wearing one name, and they are not the same. The first is isotropy. It says the universe looks the same in every direction from where we stand, with no axis, no preferred line, no direction marked out as special. The second is homogeneity. It says the universe has the same average makeup at every place, that no location is denser or emptier than any other once you look at a large enough region. These can come apart. You could imagine a universe that looks identical in all directions from one central point and yet is arranged in shells around that point, the same view outward but a very special place to stand. The cosmological principle refuses that. It insists the universe is isotropic, not only for us, but for any observer anywhere, and isotropy around every point forces homogeneity as a consequence. The universe looks the same in all directions, for everyone, with nobody at the center. The reason we cannot do without it lies in the theory we use to describe space itself. General relativity ties the shape of space and time directly to the matter inside it, and for an arbitrary, lumpy distribution of matter, its equations are far too tangled to solve for the universe as a whole. But grant the cosmological principle, and the impossible collapses into something elegant. A universe that is the same everywhere and in all directions can be captured by a single solution, governed by one number that tracks the only thing free to change, the overall scale of space. That one number, growing with time, is the expansion we have been tracing all along. The entire behavior of the cosmos, from its beginning to its accelerating present, falls out of one equation for how that single scale changes. The lumps of real galaxies become small corrections sprinkled on top of a smooth backbone. Without the principle, there is no backbone, and the corrections have nothing to correct. That single reduction buys an enormous amount, and a great deal is staked on it. The age of the universe, that clean figure of 13.8 billion years, is meaningful only because the same expansion ran the same way everywhere, giving every region one shared clock. The Big Bang as a single origin, rather than a different beginning in every neighborhood, requires the same uniformity. The very phrase "the universe," treated as one object with one history we can write down, is a privilege the principle grants us. Take it away, and you are left not with a universe, but with countless separate regions, each demanding its own description, none of them addable into a whole. The science does not merely get harder, it loses its subject. When Einstein first applied his new theory to the entire cosmos in 1917, he assumed uniformity not because anyone had measured it, but because without it the problem was hopeless. The name came later, in the 1930s, and the idea carried forward an older humility, the Copernican lesson that we are not standing at the center of things. If the Earth is not special, and the Sun is not special, then perhaps no place is, and the universe has no center and no edge to privilege one spot over another. The principle took that modest refusal to be special and made it the foundation stone of an entire science. For a long time, it was an article of faith dressed as a working assumption. One subtlety keeps the whole idea from collapsing on contact with what we actually see. The cosmological principle does not say the universe is smooth. Up close, it is anything but. You are denser than the room around you. The Earth is denser than the space near it. The galaxy is a brilliant island in a vast dark, and on every scale you can directly see, the universe is violently lumpy. The claim is only about averages taken over large volumes. Smear the cosmos over a region wide enough, and the principle says every such region should weigh the same, hold the same blend of galaxies and emptiness as every other. The lumpiness is real but local, washing out when you step far enough back. The universe is meant to be smooth, the way a beach is smooth, grainy in the hand, even from the cliff. What we can actually test is lopsided between the two halves. Isotropy we have confirmed to extraordinary precision, because the oldest light in the sky arrives at almost exactly the same temperature from every direction, matching to 1 part in 100,000 once our own motion through space is removed. The universe around us is isotropic to a degree that leaves little doubt. Homogeneity is harder, because we are pinned to one point in space and can only look outward. And looking outward is also looking backward in time, so we never get a clean present-day snapshot of a distant region to lay beside our own. Homogeneity is therefore inferred rather than directly seen. We grant that the universe is isotropic around us. We refuse to believe our location is special, and from those two together, homogeneity follows. The foundation is part measurement, part principled humility. The principle does not promise sameness at every scale, only above some scale, with lumps fully expected below it. So everything turns on where that line falls, the size above which the universe is finally obliged to go smooth and forget its clumps. If that scale is small enough, the wall is a problem. If it is large enough, perhaps there is room for it after all. That threshold, the exact size at which greatness is supposed to end, is the number we have to pin down next. The scale where the universe is finally forced to go smooth sits at roughly 300 million light-years. Below that size, the cosmos is all structure. Above it, the structure surrenders to sameness. 300 million light-years is itself staggering. Laid against our galaxy, it is 3,000 Milky Ways in a row, a span holding millions of galaxies and the great void strung between them. And yet, against the object we are chasing, it is small. The wall reaches 10 billion light-years, more than 30 times this threshold. So the threshold is where the real argument lives, and it was measured, not guessed. The way you measure such a thing is patient and almost mechanical. Pick a point in the mapped universe and draw a sphere around it of some chosen radius. Count the galaxies inside and work out the average density. Then do it again, centered somewhere else, and again across thousands of locations. For small spheres, the answer is wildly unsteady. Center your little sphere on a cluster, and it brims with galaxies. Center it on a void, and it comes back nearly empty. The density you measure depends entirely on where you happen to place the sphere. Now grow the sphere and run the whole exercise again. As the radius climbs, the swings begin to settle. The crowded regions and the empty ones start to balance inside each sphere, and the density measured from one location creeps toward the density measured from any other. The radius at which those swings finally die away, where every sphere returns essentially the same average density no matter where you center it, is the homogeneity scale. It is the size at which the universe stops caring where you stand. In a perfectly uniform universe, doubling the radius multiplies the volume by 8, and the number of galaxies inside should rise by that same factor of 8, growing as the cube of the radius, the natural behavior of anything spread evenly through three-dimensional space. But on smaller scales, galaxies are not spread evenly. They cling to filaments and shun the voids, so the count rises more slowly than the cube, as though the matter were threaded along lines and sheets rather than filling space. Widen the sphere past a few 100 million light-years, and that growth straightens out and locks onto the cube. The point where the counting begins to behave as though space is uniformly filled is the same threshold, expressed as a clean geometric fact. Below that point, matter is webbed along strands. Past it, matter simply fills the room. None of this was settled by argument. It was settled by mapping the sky, galaxy by galaxy, in surveys that charted the positions and distances of millions of them across enormous volumes of space. When the count-in-spheres test and the geometric test were run on those vast catalogs, they agreed. The swings died down, and the counting straightened onto the cube by a scale of a few 100 million light-years. The end of greatness stopped being a theoretical expectation and became a measured property of the real universe. Above a few 100 million light-years, the cosmos genuinely does forget its lumps. The exact figure carries honest uncertainty. Different surveys and different methods place the threshold anywhere from about 200 to nearly 400 million light-years, and the largest superclusters brush close enough to that line to keep cosmologists arguing over the precise value. But the disagreement is over a few 100 million light-years one way or the other. Nobody measuring the real galaxy distribution finds the smoothing scale at 1 billion or 2 billion, let alone 10. The number is fuzzy at its edge and rock solid in its order of magnitude. There is one exception to the featurelessness above that scale, and it is among the most beautiful measurements in all of cosmology. The universe carries a single built-in ruler, one faint preferred distance baked into where galaxies sit. In the first few 100,000 years after the beginning, the cosmos was a hot plasma in which pressure waves, true sound waves, rippled outward through the matter. When the universe cooled enough to turn transparent, those waves froze where they stood, leaving a slight surplus of matter in shells of one particular radius. That radius, stretched by all the expansion since, now shows up as a gentle tendency for pairs of galaxies to sit about 500 million light-years apart, very slightly more often than chance alone would allow. It is not a structure. It is a whisper in the statistics, a frozen echo of the infant universe ringing like a struck bell. And it is the only special length the large-scale universe owns. Even this one preferred scale, the deepest feature in the entire cosmic distribution, sits about 20 times below the size of the wall. So the numbers are on the table now, each of them measured rather than assumed. The universe goes statistically smooth by a few 100 million light-years. Its one built-in ruler, the echo of primordial sound, falls near 500 million. Above those scales, the cosmos is meant to be a uniform sea, the same in every direction and every place, holding no coherent thing larger than that frozen whisper. Into that supposedly featureless sea, the bursts trace one connected concentration 10 billion light-years long. The threshold and the object are both in front of us. What remains is to lay one directly against the other, and to ask, plainly, what it means when a single structure outruns the smoothing scale not by a little, but by something close to a factor of 30. Lay the two measurements against each other, and the conflict is not subtle. The universe is supposed to forget its structure above a few 100 million light-years, with its single deepest feature, the relic of primordial sound, sitting near 500 million. The wall is a coherent concentration 10 billion light-years long. It is not a few percent past the limit. It is roughly 30 times the smoothing scale and 20 times the universe's one built-in ruler. Stated in the language of measurement, the matter inside the wall is correlated, arranged in concert, across a separation where the correlation between regions should long ago have fallen to nothing. The quantity that is supposed to be exactly zero at this distance is instead pronounced and extended. That phrase, correlation across a distance, carries the whole weight of the problem. Two regions are correlated when knowing what one is like tells you something about the other, when their densities rise and fall together rather than independently. Near home, galaxies are strongly correlated. Find one cluster and you are likely to find more close by, strung along the same filament. That correlation weakens with distance and, by the smoothing scale, vanishes. Two patches of sky a billion light-years apart are supposed to know nothing of each other, their densities set independently, like two coins flipped in separate rooms. The wall says otherwise. It says that across 10 billion light-years, the densest patches are still arranged together, still part of one design. Two coins flipped 10 billion light-years apart are landing on the same face far too often. Either the coins are somehow talking, which nothing in physics permits across that gulf, or they were never truly independent to begin with. A structure stretched across a large fraction of the visible universe means the cosmos is not uniform, even on scales approaching the horizon, and the uniform solution we use to describe everything, the one shared clock, the one history, the single expanding scale, no longer cleanly applies. The standard model of cosmology is not a single equation but that entire edifice resting on uniformity. A real 10 billion light-year structure does not dent a corner of it. It pulls at the foundation beneath all of it. When the discovery was first weighed against the standard model, the question was simple. How often would a clustering this tight and this large arise purely by chance in a universe that truly is smooth on these scales? The answer that came back was a probability so small it is hard to put into ordinary words, the kind of long odds you would attach to flipping a fair coin and watching it land heads dozens of times in a row. If the universe is as smooth as the principle demands, a structure like the wall should essentially never appear in the entire volume we can see. Its mere presence in the data is the anomaly. That calculation, though, rests on the bursts being a fair and trustworthy map of the matter, and that single assumption is the most vulnerable part of the whole case. Over the same years, separate teams using entirely different objects have turned up other structures that brush against or break the same limit. A vast grouping of quasars, the brilliant cores of active galaxies, was charted spanning well over 1 billion light-years, larger than the supposed maximum and announced openly as a challenge to the smoothing scale. Another team found 9 gamma-ray bursts arranged in a ring across the sky some 5 billion light-years wide, a pattern with no easy, innocent explanation. The Sloan Great Wall, drawn from ordinary galaxies, was already pressing on the ceiling from below. No single one of these is decisive, and each carries its own doubters, but taken together they form an uncomfortable pattern. The largest things we keep finding sit at or beyond the size the model calls the absolute top, again and again, from different tracers and different teams. This is what turns a curiosity into a crisis. A single anomaly can be a fluke, a statistical accident in one corner of the sky. A repeated anomaly in independent data from independent methods starts to look less like an accident and more like something the universe is trying to tell us. If even one of these structures is real at its claimed size, the prediction the standard model makes about the largest scales is simply wrong, and only 3 escapes remain. Either the structures are illusions born of imperfect data, or our statistics for how structure grows are mistaken, or the universe at the deepest scales does not obey the uniformity we assumed. None of those leaves the model untouched. The first escape is the gentlest, and the one most cosmologists reach for first, because it asks the least of the universe and the most of our instruments. Perhaps the wall is not too big for physics at all. Perhaps it was never there to begin with, and we have been startled by a shape that our own sparse, flickering map painted out of noise. Before we are willing to conclude that the cosmos breaks its own deepest rule, we owe the data the hardest and most deflating question of all. How sure are we, really, that the wall is even there? The strongest case against a crisis in cosmology is also the simplest. There is no crisis because there is no wall. This is not a fringe stance or a refusal to face hard data. It is the ordinary caution of a field that has been fooled before, and it deserves to be put as forcefully as the case for the wall itself. Before we rewrite the laws of the universe, we are obliged to ask whether the thing breaking them is an object at all, or a shape we drew across scattered points and then mistook for something real. Begin with how thin the evidence actually is. The entire structure rests on a few dozen gamma-ray bursts, around 30 flares falling within one particular band of distance and one broad region of the sky. From those few points, spread across 10 billion light-years, a connected wall was inferred. Stretch that out in your mind. 30 markers, used to claim the largest object in the universe, each one separated from the next by gulfs that dwarf entire superclusters. 30 pins in a volume that vast is not a photograph of a structure. It is the barest sketch, and a sketch that sparse can be read more than one way. The deepest danger in reading it is one our own minds are built for. Humans are relentless pattern finders, and we will impose order on noise without ever noticing we have done it. The night sky is the oldest proof of this. The constellations look like figures, hunters and bears and hanging belts, groups of stars that seem to belong together, and they do not belong together at all. The stars in any constellation lie at wildly different distances, some near, some far, bound into a shape only by the accident of our line of sight. There is no hunter up there, only unrelated suns that happen to fall along similar directions from where we stand. The same trap waits in the burst map. A handful of flares that appear to trace a wall may be unrelated events, scattered through an immense depth, lined into a figure by perspective and chance, rather than by any physical bond between them. Then there is the problem of where we are able to look at all. Gamma-ray bursts are not detected evenly across the sky, and their distances are harder still to pin down. The detectors that catch them have uneven coverage, some regions watched far more closely than others. Worse, measuring a burst's distance means catching its fading afterglow with ground telescopes in the hours before it vanishes, and that follow-up is patchy, favoring the parts of the sky that are easy to observe and shying away from the crowded band of our own galaxy. So, the bursts with known distances are not a fair sample of where bursts actually occur. They are a sample shaped by where we happen to be pointing and able to respond. An apparent crowding of bursts in one region can reflect the geography of our own observing far more than any true crowding of matter out in space. A subtler statistical trap sits on top of that one. If you search a large sky across many slices of distance, hunting everywhere for an unusual clump, you are running an enormous number of trials. With enough trials, a striking-looking cluster will turn up somewhere purely by chance, no matter how smooth the underlying universe truly is. The honest way to judge such a find is to penalize it for every place you looked and found nothing. When the wall's significance is recomputed with that full accounting, folding in the uneven sky coverage and the many regions searched, the result weakens. What first looked like a near impossible clustering softens towards something a smooth, random universe could plausibly produce on its own. This is not a marginal objection. Independent analyses went back to the burst catalogs, applied stricter tests for genuine clumping, and accounted for the lopsided way the bursts were gathered, and they concluded that the evidence for a real, connected structure does not hold up cleanly. By those tests, the spread of the bursts is consistent with chance. The wall, on this reading, is not a forbidden object straining the laws of physics. It is a constellation, a figure our pattern-hungry analysis traced across an unfair and sparse map. The honest position cuts in both directions, and the question stays open rather than closing in either side's favor. Showing that the data are consistent with chance is not the same as showing the wall is not there. Sparse evidence can fail to confirm a real thing just as easily as it can conjure a false one. The skeptics have not proven absence. They have shown that the present data are too thin and too biased to carry so extraordinary a claim, which is a different and far more careful statement. The wall might be real and simply undersampled, or it might be a mirage. With around 30 flickers to go on, the universe has not yet told us which. What would settle it is not cleverness but more light. A far larger catalog of bursts with measured distances, spread fairly across the sky, would either firm the structure into something undeniable or dissolve it back into the smooth background. Independent confirmation from other tracers, Ordinary galaxies or quasars charted through the same enormous volume would do the same. Until then, the largest object ever claimed wears a question mark, and honesty has to leave it there. But notice what does not depend on the answer. Whether the wall is one connected thing or 30 unrelated flares, every one of those bursts went off billions of years ago, and their light has only now reached us. We are not seeing any of this as it is. We are seeing it as it was when the universe was young. And that one fact opens a problem the question of its reality never even touched. Every telescope is a time machine, and it cannot be anything else. Because light travels at a fixed speed, it always arrives carrying old news, showing each object not as it is, but as it was when the light departed. The moon you see is a second into the past, the sun 8 minutes, the nearest star more than 4 years. The rule never relaxes, and the farther out you look, the deeper into the past you are forced to see. The light from the wall has been traveling for something close to 10 billion years. We are not looking across space so much as down through time, into an era the universe left behind long before the Earth existed. Put a number on how far back, and the view turns stranger still. The universe is about 13.8 billion years old, and the light defining the wall set out when the cosmos was roughly 3 to 4 billion years old, a little more than a quarter of its present age. When that light began its journey, there was no sun, no earth, nothing of the world you are lying in tonight. The solar system would not gather out of its parent cloud of gas for billions of years more. We are seeing the wall not in the universe's maturity but in its youth, while our own origins were still unformed in the dark. The era we are peering into was no quiet backwater of cosmic history. It was the most fertile stretch the universe has ever known, the period astronomers call the cosmic noon, when galaxies forged new stars faster than at any time before or since. The cosmos then was younger, denser, far richer in cold gas, and it turned that gas into stars at a furious rate, well above the slow trickle of star birth in our own quiet age. More massive stars were being born, which means more of them were dying, which is precisely why the brilliant flares we use as markers crowd so thickly into that slice of distance. The wall, real or not, is drawn from the brightest depths of the universe's busiest morning. There is a distance subtlety that changes what the number 10 billion even means. The light has been in flight for about 10 billion years, but the region that sent it has not stayed put. Space has expanded the entire time, carrying that region steadily farther from us as its old light crept inward. So the part of the cosmos we are seeing now sits far more than 10 billion light-years away, pushed out by all the growth that happened during the journey. The 10 billion is closer to a measure of how long the light traveled than of how far the wall lies from us today. We are not seeing where that matter is. We are seeing where it was, and where it was is a place that no longer exists in the form the light recorded. Whatever the wall was when its light departed, it has had 10 billion years to change since. Galaxies have drifted. Expansion has stretched the gaps between them. Some clusters have merged, while others have been carried apart. The arrangement frozen in the light reaching us tonight may long since have rearranged into something we would not recognize, or dissolved altogether into the smooth flow of the expanding cosmos. We are studying a fossil, an imprint of a single moment, not a living object we could ever check on. And we can never check on it, because any light leaving that region now will not arrive at this spot for another 10 billion years, by which time everything here will be unrecognizable as well. A quiet strangeness sits underneath all of astronomy, and the wall only makes it vivid. There is no single present moment we can observe anywhere beyond our own immediate surroundings. The night sky is not a single still image of the universe as it is. It is an archive, each object showing a different depth of the past at once. Nearby stars a few years back, distant galaxies billions of years back, all of it layered into one view that belongs to no single instant in the history of anything. When you look up, you are not seeing the universe. You are seeing every era of the universe at once, sorted by distance, a single picture stitched together from 1,000 different epochs. For the wall, this layering is not a curiosity. It is the whole of the next problem. If the structure is real, then it was already that enormous, already stretched across 1/10 of the visible cosmos, when the universe was only a few billion years old. The vastness we have been wrestling with was not built up gradually across all of cosmic history with time to spare. It was, on this reading, already in place near the beginning, assembled inside a window far shorter than the full age we have been using to picture it. Which forces a question that has nothing to do with whether the pattern is real and everything to do with whether it is even possible. Given how slowly gravity works and how little time had passed, was there ever enough of it for anything that large to come together at all? Start the clock at the beginning and let it run to the moment we actually see the wall. By the time that light departed, only about 3 billion years had passed since the universe began. 3 billion years sounds enormous against a single human life, but against the task in front of us it is almost nothing. The question is brutally simple. In 3 billion years, could anything have gathered matter into a coherent thing 10 billion light-years across? The answer the physics keeps returning is no. Two hard limits stand in the way, and behind them lies a strangeness deeper than either. Structure in the universe grows by a slow and patient process. A region that begins very slightly denser than its surroundings pulls a little harder on the matter around it, drawing in more, growing denser, pulling harder still. Left alone, that feedback would race. But it is never left alone, because the whole universe is expanding at the same time, stretching every region apart, even as gravity tries to draw it together. The two work against each other, expansion thinning the matter while gravity concentrates it, and the result is not a runaway but a crawl. Overdensities amplify gradually, across hundreds of millions and then billions of years, never explosively. Building large structure is less an avalanche than a slow tightening, and the universe simply had not been tightening for very long. We know how gentle the starting point was, because we can read it in the oldest light. At the moment that light was set free, the universe was smooth to 1 part in 100,000, its densest regions barely a hair fuller than its emptiest. Every structure that exists had to grow from those faint seeds, amplified by gravity across all the history since, and reaching today's rich web of galaxies and voids, took most of 13 billion years of that patient tightening. At the cosmic noon where we see the wall, far less of that amplification had happened. The universe then was markedly smoother than it is now, its structures less developed, its contrasts milder. To find a coherent feature larger than anything in today's mature universe, sitting in that younger, smoother era, runs exactly backward to how growth is meant to work. The biggest things should arrive late, not early. The first hard limit is the simplest, and it comes straight from the speed of gravity. Gravity's influence does not act instantly across space. It propagates at the speed of light and no faster, the same strict ceiling that governs everything else. For a structure to be coordinated as one coherent thing, gravity has to have had time to cross it, to carry its pull from one side to the other. A structure 10 billion light-years wide would need 10 billion years just for gravity to reach across it a single time. But only 3 billion years had passed. The far ends of the wall, in that early universe, had never been in gravitational contact at all. No influence of any kind had had time to travel between them. They could not have arranged themselves into one structure, because nothing linking them had yet had the chance to cross the gap. A second limit closes the same door from another side. Set aside whether gravity could even communicate across the wall, and the matter itself would still have had to travel in order to assemble there, and matter moves slowly. Galaxies drift relative to the expanding background at speeds of only hundreds of kilometers a second, fast by any human measure but glacial against cosmic distances. Across the entire age of the universe, that drift carries a galaxy only tens of millions of light-years from where it began, never billions. Matter cannot have flowed together across 10 billion light-years to build anything, because in all of cosmic history, it has never had time to migrate even 1,000th of that distance. Whatever the wall is, it was not assembled by matter streaming into place. Put those limits together, and they force a conclusion stranger than the size ever was. If the wall is a real, coherent feature, it cannot have been built by gravity in the 3 billion years it had, nor in the full 13 billion since. Gravity could not have reached across it. Matter could not have traveled to fill it, and the slow tightening that builds every other structure could not have built this one. A coherent pattern that large, if it is truly there, cannot be something that grew. It would have to be something that was already there, imprinted into the universe from its earliest instance, before the slow work of gravity had even begun. The mystery moves from how did it form to how was it seeded, and that is a far deeper and more uncomfortable place to set it down. Seeding a correlation across 10 billion light-years before structure growth started means reaching all the way back to the initial conditions of the cosmos, to the rules that laid down its very first ripples. And there the escape routes narrow to a hard few. Either the invisible matter that does most of the gravitational work behaves in ways we have never understood, or gravity itself acts differently on the largest scales than our equations claim, or the seeds the universe began with were not the smooth, random whisper we have always assumed them to be. None of those is a small adjustment. Each one rewrites a chapter we thought was closed, and the only thing left to decide is which of them the universe is forcing us to open. The cheapest fix is still the one we have already met. Perhaps the wall is not real, and there is nothing here to explain. But suppose, for the length of this act, that it is real, that the correlation truly is out there. Then physics has to bend somewhere, and there are only 3 places it can bend. Each one is a suspect, not a verdict, and following each to its limit is more revealing than settling on any of them. The first suspect is dark matter, because dark matter is what builds structure in the first place. Ordinary matter, the stuff of stars and planets and people, makes up only about 5% of the universe. Around 27% is dark matter, an invisible substance that neither gives off nor absorbs light and shows itself only through gravity. It matters here because in the early universe, ordinary matter could not begin to clump. It was bound up with light in a hot plasma, and the pressure of that light smoothed it out as fast as gravity tried to gather it. Dark matter felt no such pressure. It began collapsing into gravitational wells, while ordinary matter was still held smooth, carving the scaffolding that all later structure fell into. So when structure forms too fast or too large, dark matter is the natural first place to look. But the suspicion runs into a hard wall of its own. You can change what dark matter is, make it warmer or colder, let it interact with itself, and you mostly alter how structure looks on small scales, inside galaxies and clusters. None of that lets gravity coordinate a region 10 billion light-years wide in 3 billion years, because the obstacle there is not what dark matter is made of. It is the speed at which any gravitational influence can travel at all. That points to the second suspect, gravity itself. Perhaps our theory of gravity, so well tested in the solar system and across galaxies, quietly fails on the very largest scales and grows structure faster than we expect. It is a serious idea, pursued by serious people. But it collides with one of the most precise measurements ever made. In 2017, two neutron stars collided and sent out two messengers at once, a ripple in the fabric of space-time and a flash of light, both crossing about 130 million light-years to reach us. They arrived within a couple of seconds of each other. After 130 million years in flight, a gap that small means gravity and light travel at the same speed to something like 1 part in 1,000 trillion. Gravity does not act instantly, and it cannot be made to. Whatever modifications you allow it, its influence still crawls at light speed, and the two ends of the wall still could never have reached each other in the time available. Bending gravity does not buy back the time the structure needs. The third suspect is the only one that can actually do the job, and it sits at the very beginning. Suppose the structure was never grown or assembled at all, but was written into the initial conditions of the universe, present in the pattern of the first ripples before gravity did any work. The standard model assumes those primordial ripples were random in a very particular way, a smooth, featureless spread with no rare giant fluctuations and no hidden long-range order, the kind of randomness that falls out of the simplest theories of the universe's first instant. If instead the seeds carried correlations across enormous distances from the outset, a coherent wall would need no time to grow. It would simply have been there from the start, and the speed of gravity would never enter the problem. This is the one escape that fits the physics, but it too runs into a measurement. The same ancient light that tells us the early universe was smooth also tells us, in fine detail, how random those seeds were, and every test of it returns the plain, featureless randomness the standard model assumed, with no trace of the large, rare features a primordial wall would require. Stand back, and the pattern across all three is the same. Each escape that could explain a real wall is blocked by something we have already measured. Dark matter changes the small scales, but not the speed limit it cannot touch. Modified gravity runs into that same limit. Now that we have clocked gravity against light to 1 part in 1,000 trillion, and primordial seeding, the only route that sidesteps the limit entirely, is hemmed in by the measured smoothness and randomness of the universe's first light. There is no comfortable door. To make the wall real, you must either find new physics that has somehow stayed invisible to every test built to catch it, or accept that one of our best-checked measurements is quietly misleading us. That is the real reason most cosmologists, weighing all of it, lean toward the gentler conclusion that the wall is a mirage in sparse data, while still refusing to close the case. It is not stubbornness. It is that a real wall would demand a revolution touching gravity, or the invisible matter, or the birth of the cosmos itself, and revolutions of that size are not granted on the strength of 30 flickers. But the live question, the one that keeps the case open, lives inside that third suspect. Everything turns on what the primordial seeds actually were, how smooth, how random, how free of any hidden order, because that is the only place a real wall could be hiding. So the path forward runs backward, all the way to the first ripples, to the faint pattern from which every galaxy and every void and every wall, real or imagined, was ever drawn. What were those seeds? And how did a nearly smooth beginning ever become a universe this full of structure at all? Everything in the universe that has any structure at all, every galaxy, every cluster, every wall, real or imagined, grew from a single faint pattern of density differences laid down at the beginning. And the origin of that pattern is one of the strangest ideas in all of physics. The seeds of cosmic structure are quantum. In the first sliver of a second after the beginning, far less than a trillionth of 1 second, the leading theory holds that the universe underwent a burst of expansion so violent it doubled in size over and over, ballooning by an unimaginable factor almost instantly. This is inflation, our best supported picture of those first moments, though not a settled fact. What makes it matter here is what it did to the smallest things. The quantum world is never still. Even empty space jitters, because the fields that fill it carry tiny, unavoidable fluctuations, a fundamental graininess that can never be smoothed away. Inflation took those microscopic quantum jitters and stretched them, in an instant, up to astronomical sizes, freezing them into the fabric of space as slight variations in density. The faint pattern that every galaxy grew from was once quantum noise, blown up until it spanned the cosmos. The largest structures in existence trace their ancestry to the smallest uncertainty there is. We can see that frozen pattern almost directly because the universe handed us a photograph of it. For its first roughly 380,000 years, the cosmos was too hot for atoms to hold together. A glowing fog of bare nuclei and free electrons through which light could barely travel. Then it cooled enough for electrons and nuclei to combine into neutral atoms. The fog cleared, and light streamed free for the first time. That light still surrounds us, stretched by expansion into a faint microwave glow arriving from every direction, the oldest light there is. Its temperature is almost perfectly even, but not quite. It is hotter in some directions and cooler in others by 1 part in 100,000, and those tiny differences are the seeds themselves, made visible. The warmer patches mark where matter was slightly denser, the cooler patches where it was slightly thinner. We are looking at the actual blueprint of everything that would later form. The pattern in that ancient light is not random scribble. It carries a precise fingerprint. Before the fog cleared, the dense plasma behaved like a fluid that could ring, gravity pulling matter inward while the pressure of trapped light pushed it back out, setting up sound waves that surged through the early universe. When the cosmos turned transparent, those waves froze in place, leaving a regular pattern of preferred sizes stamped into the density of matter and into the temperature of the light. Measure the sizes of the hot and cold patches across the sky, and they gather around specific scales, exactly the scales the ringing predicts. This is why we can speak with such confidence about what the seeds were like. The fingerprint matches the theory to extraordinary precision, telling us the seeds were smooth, nearly equal in strength on every scale, and random in the simplest possible way. The starting pattern is not a guess, but a measurement. From that nearly smooth start, gravity went to work, and the way it builds is what gives the universe its shape. A region that began slightly denser pulls matter toward it, but the collapse does not happen evenly in all directions at once. Matter falls in first along whichever direction is most compressed, draining out of the emptiest regions and piling into broad, thin sheets. Then, within those sheets, it slides along them and gathers into long, dense filaments, threads of galaxies strung across the dark. Where filaments cross, matter pools into the richest knots of all, the great clusters, and the regions left behind, drained of their matter, open into vast empty voids. Run that process across billions of years, and a nearly featureless beginning organizes itself into something that looks unmistakably like a web. Sheets and filaments and dense nodes wrapped around enormous bubbles of emptiness. The cosmic web is not imposed from outside. It falls out of gravity acting on those quantum seeds, and computer models that start from the measured seeds and let gravity run reproduce exactly this web, matching the real sky. And a wall is not an absurd thing to find, because walls are part of what the web naturally makes. The broad sheets, the first features to form as matter collapses, are walls, flattened concentrations of galaxies spread across the sky. Real ones have been charted and named, great walls of galaxies hundreds of millions of light-years long, exactly the sheet-like features the web is supposed to produce. A wall in the cosmos is not an exotic claim. It is one of the basic shapes the universe builds out of its seeds. But the web builds its walls only up to a size, and no further. The sheets and filaments top out near the smoothing scale, a few 100 million light-years, because that is as far as the seeds carry any order and as far as gravity has had time to organize. The Hercules-Corona Borealis Great Wall, if it is real, would be a wall of that familiar kind stretched to 30 times the size the seeds and gravity together can account for. Everything we have just traced, the quantum origin, the measured fingerprint, the patient growth, says walls should exist and says they should stop long before this one does. So the question narrows to something concrete and answerable. How was this particular wall actually found? From how many flares and by what method? And how much weight can that method truly bear? The largest structure ever claimed was not found through a telescope pointed at the sky. It was found in a list. A little over a decade ago, 3 researchers, Istvan Horvath, John Hakila, and Zsolt Bagoli, sat with a catalog of gamma-ray bursts and one stubborn question. They wanted to know whether the bursts were sprinkled evenly through the universe, the way the cosmological principle says everything should be, or whether they betrayed some hidden clumping. What they found in that list became the Hercules-Corona Borealis Great Wall, and the way they found it matters as much as the thing itself, because the method is exactly what the whole argument has hinged on ever since. Their raw material was a few hundred gamma-ray bursts, the only ones in the entire record whose distances had been pinned down. A burst flares and fades in seconds, but its afterglow can linger long enough for a telescope to catch its spectrum and read its redshift, and from the redshift comes the distance. Most bursts are caught too briefly, or too far from a ready telescope, for that follow-up to happen. So, out of the thousands detected, only a few hundred carried a trustworthy depth. That modest list was the entire map of the deep universe they had to work with. The idea was clean. Sort the bursts by distance into slices, each slice a shell of the universe at a particular depth. Then, within each slice, ask how the bursts are spread across the sky. If the universe is smooth and the bursts trace it fairly, every slice should look much the same, the flares scattered evenly in all directions with no favored patch, the very definition of an isotropic sky. A real structure, by contrast, would show itself as a crowding, too many bursts piled into one direction at one particular depth, more than an even sprinkle could explain. They ran statistical tests on each slice, comparing the actual spread of bursts against the spread a perfectly uniform universe would give, and measuring how unlikely the real pattern would be if uniformity held. Slice after slice came back ordinary. The nearer shells, the farther shells, the bursts lay across them evenly, exactly as expected, no direction favored over any other. Then, one slice broke the pattern. In the shell, at a depth where the light is around 10 billion years old, the bursts were not spread evenly at all. Roughly 30 of them were bunched into a single broad region of the sky, far more crowded than any even scattering should allow. The tests put a small number on it, a probability of well under 1%, that a smooth, uniform universe would clump its bursts that tightly in that shell by chance alone. One slice out of many had failed the test for uniformity, and failed it hard. The crowded patch lay in the direction of 2 constellations, Hercules and the small ring of stars called Corona Borealis, and the structure took its name from them, following the old habit of naming great walls after the part of sky they occupy. The name carries a quiet trap. Those constellations are patterns of nearby stars, a few hundred to a few thousand light-years away, sitting inside our own galaxy. The wall has nothing to do with them. It lies 10 billion light-years beyond them, in the same line of sight purely by accident. The constellations are only an address written on the foreground, marking the patch of sky you would look toward, not the neighborhood the structure lives in. The size came not from imagination, but from geometry. The crowded bursts spanned a wide angle across that patch of sky, and they sat in a shell with real depth, a range of distances rather than a single thin sheet. Take the angle the clump subtends, set it at the distance its redshift implies, and add the depth of the redshift band, and the physical extent of the region falls straight out of the arithmetic. The numbers that came back ran into the billions of light-years across, with the longest dimension reaching the 10 billion that put the structure into headlines. Nobody chose that figure for its drama. It was simply what the angle and the distance and the depth multiplied out to. The largest number in cosmology emerged from a clump of 30 flares and some careful trigonometry. The three who found it were careful about what they claimed. They did not announce a confirmed object that shatters physics. They described a possible structure, flagged its tension with the smoothing scale, and left the door open, because they understood better than anyone how thin their map was. And that thinness is the whole vulnerability, the same trick that let them see anything at all at 10 billion light-years, using rare, bright flares as stand-ins for matter, is the trick that makes the result so fragile. The map holds only 30 pins, and the pins were gathered unevenly, wherever a telescope happened to catch an afterglow in time. So the honest next step is not to celebrate the wall, and not to dismiss it, but to interrogate the ruler itself. How much can a structure built from 30 unevenly scattered flares really be trusted? And what becomes of the wall when you press hard on every weakness in that flickering, incomplete map? A ruler is only as good as the thing it measures, and the trouble with gamma-ray bursts is that they do not measure what we actually want to know. We want a map of matter. What the bursts give us is something else, related but bent, and the bend is where the wall may be hiding. A burst marks the death of a massive star, and massive stars are short-lived, burning out within a few million years of forming. So a burst does not flag where matter is. It flags where matter was busy making new heavy stars at that moment. The bursts trace star formation, not mass, and those two are not the same map. Consider what that distinction does. A vast, ancient region packed with old stars and dark matter, immensely massive but no longer forming new giants, would produce almost no bursts at all. It would be heavy and all but invisible to this ruler. Meanwhile, a smaller region caught in a frenzy of new star birth would light up with flares far out of proportion to its actual mass. The burst map brightens wherever the universe is fertile and goes dark wherever it is merely massive. So reading it as a map of matter quietly overweights the busy regions and erases the quiet ones. The clumps it shows may be clumps of star formation, not clumps of mass. The bias runs deeper than activity, down into chemistry. The particular bursts we see across most of the universe, the long ones from collapsing giant stars, strongly prefer a specific kind of birthplace, one poor in heavy elements. A star rich in heavy elements sheds mass through fierce winds and tends to spin down before it dies, and the violent jet-launching collapse that makes a burst becomes far less likely. In gas that is chemically pristine, low in everything heavier than helium, that collapse proceeds and the burst fires. So the flares do not even sample all star-forming regions fairly. They favor the chemically young, metal-poor pockets of the cosmos and pass over the enriched ones. The ruler is selective twice over, blind to massive quiet regions and partial to a particular chemistry among the active ones. Distance adds a third tilt. At 10 billion light-years, only the most luminous bursts are bright enough to be caught and measured at all. So the deep sample is skimmed from the very brightest events, not a fair cross-section of them. The faint majority at that depth simply never register. What survives into the catalog from so far away is a rare, bright, chemically biased subset of an already biased tracer. And that thin population is what the wall was drawn from. With only about 30 points marking a structure across 10 billion light-years, the map is not merely sparse, it is statistically jumpy. Scatter 30 points at random through a large volume and they will never look smooth. By pure chance, they fall into apparent clusters in some places and gaps in others, knots and voids that mean nothing, simply because 30 is far too few to average out. The human eye seizes on those accidental knots as patterns, and even careful tests can be fooled by them, because a true clump and a random crowd of 30 points can look nearly identical. Sparse random data does not look random. It looks structured, and that false structure is exactly what a real structure would look like as well. There is one more soft spot, and it is methodological. How significant the clump appears depends heavily on which statistical test you choose to judge it. Tests for clustering on the curved surface of the sky carry known subtleties, and reasonable people making reasonable choices have drawn meaningfully different answers from the very same bursts, some finding the clump striking, others finding it unremarkable. When a result swings with the method used to weigh it, that is a sign the data are not speaking loudly enough to overrule the choices of the analyst. A robust structure announces itself no matter how you test it. This one does not. None of this proves the wall is an illusion, and that has to be said plainly. A biased, sparse, jumpy ruler can still occasionally point at something real. But stack the flaws together, the blindness to quiet mass, the preference for metal-poor starbirth, the skimming of only the brightest events at depth, the false clumping of small numbers, the sensitivity to method, and you are left with a measuring tool that could manufacture a wall-shaped pattern out of nothing but its own crooked design. The burden falls on the wall to survive all of that, and with 30 flares it cannot yet carry that burden. So to learn what the largest scales of the universe truly look like, we should set the flares aside and turn to the tracer that escapes most of these faults, the one mapped not from 30 rare deaths, but from millions of ordinary galaxies. The real large-scale structure of the cosmos has been charted in remarkable detail, and it has a definite shape. What does that better map show, and does anything in it ever rise to the scale of a wall? The trustworthy map of the universe's structure was not drawn from a handful of flares. It was built from millions of galaxies, each one placed in 3 dimensions by measuring its distance the same way we measure a burst's, through the redshift of its light. Point a telescope at a patch of sky, record the redshift of every galaxy in it, and you turn a flat smear of dots into a true depth map, galaxies set at their real distances rather than pasted onto one backdrop. Do that for millions of them, across wide swaths of sky, and the actual skeleton of the cosmos emerges. It is one of the great mapping achievements in the history of science. When the first of these 3-dimensional slices was assembled, in the 1980s, it delivered a jolt because the galaxies did not lie where most had expected. People had imagined them scattered fairly evenly through space, like pepper shaken across a tablecloth. Instead, they traced thin, curving walls wrapped around great empty hollows, as if the matter of the universe were smeared over the skins of enormous bubbles with almost nothing inside them. One early map became famous for a chance figure in the data that looked like a little stick man standing among the galaxies. The emptiness was the real surprise. Most of the volume of the universe, it turned out, is void. Vast, rounded hollows where galaxies barely tread, while the galaxies themselves are confined to the thin films and threads between those hollows. Larger surveys that followed, charting first hundreds of thousands and then millions of galaxies, confirmed and sharpened the picture into what we now call the cosmic web. The architecture is the same everywhere we look across the well-mapped nearer universe. Enormous voids, many tens and even hundreds of millions of light-years across, take up most of the room. Around them, galaxies gather into flattened walls. Where walls meet, they fold into dense filaments, and where filaments cross, the great clusters sit at the knots. The whole thing resembles a sponge, matter drawn onto its surfaces and edges, while the hollows stand empty. This is the real large-scale structure of the cosmos, mapped now in exquisite detail, not inferred from 30 points, but pinned down by millions of them. The Webb does build walls, and we have measured the largest of them with confidence. The first Great Wall found in those early surveys stretches something like 500 million light-years along its length, a true sheet of thousands of galaxies. A later survey turned up a still larger one, a wall of galaxies reaching about 1.5 billion light-years, the biggest structure ever confirmed from a dense map of ordinary galaxies. These are real, and they sit right where theory said the largest things should sit, pressing against the limit, brushing the ceiling without clearly breaking through it. Map the universe from millions of galaxies, and the largest coherent things climb to a few hundred million light-years, with rare outliers reaching past 1 billion, and then the structure gives out. Take any large enough box of the well-mapped sky, and it resembles every other, just as the smoothing scale demands. Set that beside the wall, and the disagreement is stark. The reliable map, drawn from millions of tracers, says coherent structure tops out near 1 billion light-years, and the universe goes smooth beyond it, exactly as the seeds and gravity predict. The Hercules-Corona Borealis Great Wall, drawn from 30 flares, says there is a coherent thing at 10 billion, 30 times past where the trustworthy map falls silent. When a sturdy measurement and a fragile one point in opposite directions, the sturdy one usually wins, and the sturdy one here says the largest scales are smooth. There is a catch that keeps this from settling the matter. The galaxy map is superb, but it is shallow compared to the flares. Cataloging millions of galaxies in 3 dimensions works beautifully in the nearer universe. But ordinary galaxies grow too faint to chart in those numbers long before 10 billion light-years. At the very depth where the wall is claimed, our magnificent galaxy map thins almost to nothing, which is precisely why the rare, brilliant bursts were pressed into service out there in the first place. So the trustworthy map reassures us about the rules close to home, where it confirms them again and again, and then falls quiet exactly where the wall sits, in the undercharted deep. The Webb is the true frame of the universe, the structure everything else hangs upon, and we are a single point somewhere inside it. Where, precisely, do we stand in all this foam? And what does our own position feel like once we finally know it? Find yourself on this map, and the first thing to notice is how unremarkable your address is. Start from the Earth, climb to the Sun and its planets, widen out to the Milky Way with its hundreds of billions of stars, then to the local group of galaxies our galaxy belongs to, and finally to the supercluster that holds them all. At every step you might expect to be moving towards some grand center, the way a small town sits within a county within a capital region. The universe offers no such center. We do not sit at a node of the cosmic web, in one of the dense clusters where filaments meet and galaxies crowd. We sit out toward the edge of our supercluster, on a quiet thread, in a thoroughly ordinary spot. It may be more ordinary than ordinary. There is growing evidence that our galaxy lies inside a relatively empty stretch of the cosmos, a region thinner in galaxies than the universal average. A modest local emptiness right beside us has been charted for decades. Beyond it, some studies argue, sits a far larger underdense region, a hollow perhaps 2 billion light-years across, in which the Milky Way is embedded, where matter runs maybe a fifth below the cosmic mean. That larger void is still debated, because gauging the density of a region from inside it is delicate work. It has been taken seriously, partly because it might ease a stubborn disagreement over how fast the universe is expanding, with the nearby cosmos seeming to fly apart slightly faster than the distant cosmos predicts. A great hollow around us could tilt those measurements. Whether or not the grand void holds up, the smaller picture is plain. We are not in a crowded quarter of the universe, we are in one of its quieter rooms. Our supercluster itself was only properly mapped a little over a decade ago, and the way it was mapped says something about where we sit. Astronomers traced not just where galaxies are, but which way they are drifting, the slow flows of whole galaxies through space. They drew the boundary of our supercluster, the way a hydrologist draws a watershed, by following which way the water runs. Every galaxy whose motion tends toward one common gravitational focus belongs to the same basin. By that rule, our galaxy sits within an enormous basin of flow, a supercluster spanning some 500 million light-years, all of it drifting toward a shared deep point, a distant mass concentration astronomers call the Great Attractor. And once again, we are not at that focus. We are far out near the rim of the basin, sliding slowly inward toward something we will never reach. We feel none of this, but we are moving, and quickly. The whole local group is being carried through space at something like 600 kilometers a second relative to the ancient background light that marks a kind of cosmic rest. That is fast enough to cross the width of the Earth in about 20 seconds, and it is steady and entirely unfelt, a silent fall toward a far-off gathering of mass. We are not parked anywhere in the cosmic web. We are in slow free fall across it, drawn by the pull of structures so distant we can barely chart them. The space we fall through is almost unimaginably empty. The nearest star to the Sun is more than 4 light-years off, and the nearest large galaxy, Andromeda, floats 2.5 million light-years away. Average the matter of the universe across all that void, and it comes to only a few atoms in every cubic meter, a vacuum far thinner than anything we can make in a laboratory. The galaxies, for all their billions of stars, are rare bright knots in a darkness that is overwhelmingly the main ingredient. We live inside one of those rare knots, on a quiet thread, near the edge of an ordinary basin, perhaps inside a great soft hollow. Some people find that picture frightening, the off-center smallness of it, the silent fall towards something unreachable. Others find it the opposite. There is no edge we are clinging to, no special burden of being the center of things, no crowded chaos pressing in. We are just a small, steady place in a vast, quiet structure, carried where the structure takes us. The same facts that shrink us also set us down gently. For most of history, we place the Earth at the center of everything. Then the Sun, then our own galaxy, each time certain we had found the middle, each time discovering we were further out and less central than we had thought, in a universe larger and lumpier than the smooth, orderly cosmos we kept expecting. The wall, real or not, is the latest jolt in that same long demotion. So the question pulling us forward is not only where we stand, but how our entire picture of the universe kept shifting underneath us, from something smooth and built around us into something vast, structured, and indifferent to where we happen to be. How did we travel from the one to the other? A century ago, almost everything we now take for granted about the universe was wrong, and wrong in the same direction. The universe was thought to be smaller than it is, smoother than it is, and far more settled than it is, with ourselves somewhere near the middle of it. Each of those beliefs has since fallen, and they fell in a particular order. Each collapse clearing room for the next. The story of how we learned the universe is vast and lumpy is also the story of how we kept being humbled. For a long time, our galaxy was the universe. The Milky Way, with its great wheel of stars, was assumed to be all there was, floating alone in an empty dark of unknown extent. There were faint spiral smudges scattered across the sky, the so-called nebulae, and no one could agree what they were. One side held that they were clouds of gas inside our own galaxy. The other held that they were separate galaxies in their own right, island universes impossibly far away. The entire scale of the cosmos hung on which side was correct, and about 100 years ago the two views met in a famous public debate that settled nothing because no one yet had the measurement to decide. The measurement came a few years later. By tracking a special kind of pulsing star whose true brightness can be read straight from the rhythm of its pulse, astronomers finally pinned down the distance to one of those spiral smudges, the one in Andromeda. It was not a cloud inside our galaxy. It lay far beyond it, a separate galaxy of its own, 2.5 million light-years away. In a single stroke, the universe expanded past all recognition. Our galaxy was not the universe, but one island among countless others, and the faint smudges everywhere were island galaxies receding into a depth no one had dared imagine. Measuring the light of those newfound galaxies showed that nearly all of them were rushing away from us, and the farther off they lay, the faster they fled. The universe was not the still, eternal stage everyone had pictured. It was expanding, every galaxy drifting from every other, which meant that, run backward, it had been smaller and denser in the past, and had a beginning. In a few short years, the cosmos went from a single fixed galaxy to an expanding sea of galaxies with a history and an origin. But one old comfort survived these upheavals. Even as the universe grew enormous and dynamic, the galaxies filling it were assumed to be sprinkled fairly evenly through space, with no grand pattern to them. The cosmological principle, the faith that the universe is the same everywhere on large scales, carried over intact, now applied to galaxies instead of stars. The picture was bigger and stranger than before, but it was still smooth. Whatever lumpiness existed was thought to be minor and local, washing out into uniformity the moment you stepped back far enough. That last comfort gave way only a few decades ago, when astronomers began measuring distances to thousands of galaxies and assembling the first true three-dimensional maps. The galaxies were strung along walls and filaments wrapped around enormous empty voids, organized on scales far larger than anyone had expected structure to reach. The universe was not a smooth sea with minor ripples. It was a vast, intricate web, lumpy and patterned across hundreds of millions of light-years. The old assumption of large-scale smoothness, which had survived the discovery of galaxies and the discovery of expansion, finally broke against the simple act of mapping where the galaxies actually sit. What replaced it is the picture we hold today, and it is a careful compromise rather than a clean victory for either side. The universe is truly lumpy, woven into the web, on every scale up to a few 100 million light-years. But above that scale, the lumpiness does finally average out, and the old principle holds after all, no longer as a claim that the universe is smooth everywhere, but as a measured fact that it becomes smooth once you look across large enough volumes. Both the lumpiness and the smoothness turned out to be real. They simply live on different scales, with the end of greatness as the hard-won border between them. Stand back from the whole century, and one rhythm repeats. Again and again, the universe turned out to be larger than we assumed, and structured further out than we believed possible. And each time we had to push the boundary of expected smoothness outward to fit what we found. The wall and the other oversized structures beside it sit exactly on the present edge of that rhythm. They press on the latest version of the boundary, the few 100 million light-year smoothing scale, asking whether even that hard-won line will hold or will have to be moved once more. This is not a model collapsing. It is a model being tested at its frontier, the same way it has been tested and refined at every frontier before. The honest question is not whether physics is broken, but whether the edge of the smooth universe truly lies where we have drawn it. We are standing right at the edge of what our data can tell us, where the galaxy maps thin out, where the flares are too few, where the answer to the largest question is, in plain honesty, that we do not yet know. That phrase, "we do not know," is not a failure or an embarrassment. In science, it is a particular and valuable place to stand, with a texture all its own. because there is a real difference between an open question and a manufactured mystery. What does it actually mean to say we are standing at the edge of the data? Every science has a line running through it, and most of the interesting questions live right on that line. On one side is what we have measured. On the other is what we have inferred from those measurements, the conclusions we have built on top of the raw numbers. The edge of the data is exactly that line, the place where measurement ends and inference begins. And the honest scientist always knows which side of it any given claim sits on. The wall sits right on the line, half measured and half inferred, which is the whole reason it is so hard to settle. Sort the pieces, and the line becomes sharp. We have firmly measured the positions of those gamma-ray bursts on the sky, and we have firmly measured their distances from the redshift of their afterglows. Those are real numbers, checkable and solid. What we have not measured is a structure. A structure is something we inferred, the conclusion that those scattered points belong together as one connected object, rather than simply falling near each other by chance. The points are data. The wall is an interpretation laid over the data, and a sparse set of points can support more than one interpretation. So when we say we do not know whether the wall is real, we are saying something precise. The measurements are sound. It is the inference resting on them that the measurements are too thin to secure. That is what makes this an open question rather than a mystery. It points at the data that would settle it, and it makes predictions that future measurements can confirm or destroy. A manufactured mystery does the opposite. It feeds on the absence of data, dodges every test, and grows loudest precisely where the evidence is thinnest. The wall is an open question in the strict sense because it tells us exactly what would resolve it. Gather many more bursts with measured distances, spread fairly across the sky, and the overdensity will either sharpen into something undeniable or melt into the smooth background. Chart ordinary galaxies or quasars through that same deep volume, and if the wall is real, they should crowd there as well, while if it is a mirage, they will not. The claim makes predictions and can be killed by evidence, which is the signature of a real scientific question and not an empty riddle. The catalog of bursts with trustworthy distances grows only slowly, by a handful of deep ones in a good year, so this is not a question that resolves next week, but it will resolve as the map fills in. When a body of thin data is consistent with two explanations, one that leaves our well-tested physics intact and one that demands tearing it down, the reasonable lean is toward the explanation that asks for less. This is not a law of nature, but a rule of good judgment, the principle that we should not pile up extraordinary claims beyond what the evidence forces on us. By that rule, the simpler reading, that 30 flares clumped together by chance and bias, is favored until the data grows strong enough to compel the harder one. But favored is not proven, and the whole discipline lies in keeping that distinction. We have not shown the wall to be false. We have shown that it is not yet supported, and we lean against it for now because parsimony asks us to, not because the case is closed. Suspended judgment, leaning gently toward the simpler answer while holding the door open, is the honest posture, and it is harder to keep than either confident belief or flat dismissal. Most cosmologists, weighing it all, doubt the wall is a real structure, and their doubt is not stubbornness or a failure of imagination. It rests on three honest things at once. The data are too sparse to carry the claim. The alternative, a real wall, would require overturning several measurements we trust far more than 30 flares. And the simpler explanation has not yet been ruled out. None of that amounts to certainty. It is calibrated doubt, which is the most a careful mind should offer when the evidence is this thin. There is something larger here, even past the wall itself. The thing the wall threatens is not a minor detail, but the cosmological principle, the assumption of large-scale sameness that we adopted in part because it made the universe solvable at all. Probing that assumption at the edge of the data is not a crisis. It is exactly what a healthy science does with its own foundations, refusing to treat even its most convenient beliefs as beyond question. The willingness to say we do not yet know whether our deepest assumption holds, and to mean it, is not weakness. It is the engine that has pushed the boundary outward at every step of the last century. And the edge of the data is not a wall we have slammed into. It is more like a shoreline. Behind us lies the lit, well-charted nearer universe, mapped galaxy by galaxy. Ahead lies a dark and enormous ocean, the deep cosmos at the distances where the wall is claimed, almost entirely unsurveyed. We have lit only the smallest fraction of it, with a scattering of rare flares and a handful of the brightest distant objects. The overwhelming majority of the volume out there has never been charted at all, so a question presses in from past the shoreline, quieter and stranger than whether this one wall is real. If the largest thing we have ever glimpsed sits right at the limit of our sight, what else might be waiting out in that unmapped dark, larger and stranger than anything we have yet had the reach to find? We have charted almost none of the deep universe, and it is easy to mistake the maps we do have for the territory itself, the well-surveyed region, where we have placed millions of galaxies in 3 dimensions, is a relatively shallow bubble around us. Beyond it stretches the vast deep, the distances where the wall is claimed and far past them, holding somewhere between a few 100 billion and a couple of trillion galaxies, the overwhelming majority of which have never been individually charted or placed. We have detailed maps of a thin shell and rough sketches of everything else. The deep universe is, in any honest accounting, mostly unexplored. The history we traced offers a tempting guide to what might be out there, and it has to be handled with care, because it is a pattern and not a proof. Every time our reach extended, we found structures larger than the limit we had assumed just before. The galaxy gave way to the supercluster to the Great Walls, the walls to claims like this one. If that pattern simply continues, the deep dark should hold structures larger and stranger than anything yet seen, with the wall merely the first faint glimpse of a hierarchy that keeps climbing. But that is induction, the expectation that the future will rhyme with the past, and induction can fail. The pattern of ever larger finds could be real, or it could be an artifact of our methods, the same pattern hunting that may have conjured the wall, repeated at each new depth. Everything we measured about the seeds and the smoothing scale says the hierarchy should have a top. If the cosmological principle holds, and above the smoothing scale all our best data say it does, then the deep universe, once properly mapped, should look like the nearer one, a web of walls and filaments up to a few 100 million light-years, and smooth, featureless sameness above that. There should be no ever larger giants waiting, because the seeds carry no order on those scales, and gravity has had no time to build any. So the intuition that bigger things must be hiding out there runs directly against our best physics. The physics predicts the opposite, that the deep will turn out reassuringly ordinary, full of the same web we already know. Set the pattern and the physics side by side, and the likeliest future is fairly clear, though not certain. As deeper maps fill in, the apparent giants we keep stumbling on, the wall, the great ring of bursts, the sprawling group of quasars, will most probably fade, dissolving under better data into the smooth background the principle demands. They would join the long list of cosmic structures that looked momentous when the data were thin and shrank to nothing once the data improved. That is the quiet bet most of the field is making. The less likely possibility, the one that cannot be dismissed, is that the principle is truly incomplete, that there really is order on scales we cannot yet explain, and that the giants are early signs of it. New surveys now beginning, charting tens of millions of galaxies far deeper than before, will push hard on exactly this question over the coming years. There is one more layer to the deep, and it is the strangest, because it lies past not the limit of our effort, but the limit of sight itself. The observable universe, that bubble 93 billion light-years across, is not the whole universe. It is only the part whose light has had time to reach us. The true universe extends well beyond it, possibly without end, and out there, past the horizon of everything we can ever see, there are almost certainly structures larger than our entire observable bubble. We will never map them, not for any lack of instruments or patience, but because the light that would carry their image has not had, and given the geometry of an expanding cosmos may never have, the time to cross the gap. Some of the universe is hidden from us by distance. The rest is hidden by the speed of light and the age of the cosmos, sealed off as surely as the past is sealed away from the present. And the hidden part is slowly growing, not shrinking. Because the expansion of the universe is speeding up, the most distant galaxies we can see are accelerating away from us, drifting toward the day when their light can no longer reach us at all. Far from opening wider, the window onto the deep is gradually closing. The cosmos we can observe will hold less and less as time goes on, not more. In the long reach of the future, observers will see a smaller universe than we do, the great structures slipping one by one past the edge of visibility. We may be living in something close to the best era there will ever be for seeing far. So the deep dark holds three kinds of unknown at once. The first is what we have not mapped, but could. The deep volume still waiting for better surveys. Beyond that lies what we might find when we get there, giants that will probably fade against a principle that will probably hold. And beneath both sits what we can never reach, the structures sealed forever past the horizon of light. It is a great deal of darkness to hold in mind at once, and there is no need to hold all of it tonight. The largest questions will still be there, patient, long after this hour. For now it is enough to have walked out to the edge of the map, looked honestly into what lies past it, and then turned, gently, back toward the small, lit, certain place where you actually are. At the start of tonight, we shrank our galaxy down to a single grain of sand on an empty beach, set beside it a thing that might stretch 10 billion light-years, and asked one question: how big is too big for the cosmos to hold? We can answer it now, honestly, and the honest answer is gentler than the question sounded. We do not fully know. And that turns out to be the right place to arrive, not a failure of the journey, but its true destination. Look back at the ground we crossed. We climbed the ladder of scale until our whole galaxy became a fleck. We found the quiet rule the universe is supposed to obey, the sameness on the largest scales that lets us describe it at all. We met the wall pressing against that rule, and then we met the honest doubt that it is there at all. Drawn from only 30 rare flares across an unfair and flickering map, we followed the problem of time, and the seeds the cosmos grew from, and the great web those seeds became, and we found our own small place out near the edge of it. What settles out of all of it is not a verdict, but a clear and livable picture. The largest scales of the universe, as far as we can trust our maps, are smooth. Below a few 100 million light-years, the cosmos is all web and void, and above it, the lumps average away into the sameness the old principle always promised. The wall is most likely a mirage in thin data, though it has not been ruled out, and somewhere out in the deep, the question waits quietly for better light to settle it. There is a turn in all of this that is easy to miss, folded inside the smallness. The same faint ripples that might or might not have arranged a wall 10 billion light-years across are the ripples that arranged everything else, including the matter that became this planet and the atoms that became you. We are not separate from the structure we have been studying. We are a small knot in the same web, grown from the same quantum seeds, made of the same matter the bursts mark when it dies. And in this one small knot, on a quiet thread, near the edge of an ordinary basin, The universe has done something it does almost nowhere else we know of. It has grown a part of itself that can look back at the whole and try to measure it. The cosmos that makes us feel so small is also the thing doing the looking through us. So the smallness was never the threat it first seemed. We are tiny and off-center, and falling slowly through a structure far too large to picture. But we also carry, in a few pounds of thinking matter, a working map of that structure out to the edge of sight, along with an honest account of where the map runs out. To understand the shape of your own place, and to know clearly the boundary of what you understand, is not a small thing to hold. It is close to the most a mind can do. And it asks nothing further of you tonight. The wall does not need you to decide it. The question is in careful hands and will keep patient for as long as it takes the light to arrive. There is nothing out there in all that dark that you have to carry into sleep. Let the scale fold back down now, the way we built it up at the start, only running the other way. In from the unmappable dark, past the great web and its voids, past our quiet supercluster and our ordinary galaxy, inward to the sun and its small blue planet, down into one room where the air is still and the night is doing the simple, ancient thing that nights have always done. The 10 billion light years are still out there, exactly as they were, asking nothing of you. And you are here, small and warm and certain, which is its own kind of enough. Thank you for spending these hours out at the edge of the universe with me, and for bringing the one thing the deep dark cannot supply on its own, a quiet, curious mind willing to look honestly at something far too large to hold. It has been good company. Rest now. The universe will keep its vast questions safe until you wake, and they will be no less wonderful in the morning for your having set them down tonight. Sleep well.